Hello and good day, geometry. It is good to be with you this afternoon. Going over CO61, talking about the properties of chords. We first learned about chords in 59, and we said that it is a segment that is contained within a circle. It goes from one point on the edge of a circle to another point on the edge of a circle, but it's a segment, so it doesn't go past the circle. It's measurable. And it turns out there's a whole bunch of things with chords that we care about, or at least that we can use, whether or not we care about them. So before we get that, though, I want to go over your assignment, just to give you the answers here, so you know whether or not you are doing things correctly. Hopefully I don't get any of these wrong as I go over them. So arc TQ, coming from a central angle, we did this one in class together here. Arc TQ, that is going to be 120 degrees, equal to the measure of its central angle. QRT, and so here we have a major arc going from point Q through point R all the way up to T. And we talked about a couple different methods that we could find this, but probably the most efficient is that if we know there are 360 degrees in a circle, and the part that we don't want up top here is 120, then 360 minus 120 will give us the part that we do want, okay, 240. I should put the degree symbol there to be most correct there. So TQR. TQR is, using the red so I stand out. Never mind, I'll stick to green. TQR coming around here, that is 180 degrees. TR is the diameter of the circle, and so the diameter will form a semicircle 180 degrees. Arc QS. You know what, kind of just make our lives easier here. Let's get that missing angle. So 360 minus the three angles that we have, minus 60 minus 80, means this is going to be 100 here. So arc QS, using the arc addition postulate, 100 plus 60 is 160 degrees. Next one, arc TS, okay, 80 degrees there. And finally, arc RST, from R through S up to T. Well, that's also a semicircle. It is the other half of the circle, so also 180 degrees. Let's see what we can do with this one over here on the right. I've got vertical angles here, so I can mark that one 70. EB being a diameter of a circle, I can take 180 and subtract 70 and subtract 45, and that leaves me with 65 degrees there. And then AC also being a diameter, with BFC here being 70, that's going to make this 110. So if I kind of slice this right through the middle with AC here, I've got 180 degrees on one side and 180 degrees on the other side. If I also slice it using diameter EB, I've got 180 degrees up top and 180 degrees on the bottom. So it all fits out. And having those other arc measures labeled will really help us as we kind of go through and basically just, combine all the pieces we need. So arc BC right here, that's going to be 70 degrees. Next one, arc DC. And again, I know these are all, the shortest possible distance from D to C, because it is a minor arc. It's 2 letters, not 3 or more. Oops, I'll drop my calculator there. So DC is going to be 65 degrees there. Arc DB, redraw that. Arc DB is going to be the sum of 65 and 70, so 135. AE here, 70 degrees. Arc AD, just kind of continue this on down to D, 70 plus 45 is 115 degrees there. And then ABC, from point A through B all the way to C, that is a semicircle, so that's going to be 180 degrees. Arc ACD, so I could have just continued that. A through C to D. So I've got my ABC, my 180, now plus 65, 245 degrees. I could also started with 360 and subtract 70 and subtract 45 to get to 245 degrees there. And finally, EAC this is a big one. We go from point E all the way through point A and over to C. So you could do it 70 plus 110, or you could do 360 minus 45 minus 65. Either way, I believe we end up with 250 degrees there, 250 degrees. So those are your answers for CO60. If I made any errors, I'm sure you will gladly let me know. But onward and forward to CO61, talking about chords. I promised someone that since I didn't get this posted Thursday, that I would not assign any book homework since you probably didn't bring your book home. So it will just be this page that you have to do for homework. A couple of theorems to write down about chords. Okay. Where's set my marker down here? Okay. Theorem 10.3 says that in a circle, okay, if we have two congruent chords, looks like a basketball or a baseball maybe, in a circle, if we have two congruent chords, we can conclude that their arc measures are also congruent. Okay, chords dealing with measurement length, arcs dealing with degrees. But if we have A, B, C, and D here, Theorem 10.3 says that if AB is congruent to CD, then arc AB will be congruent to arc CD. Okay, so if those segments, those chords are congruent, the arcs will be congruent as well. Okay, Theorem 10.4 and 10.5 are kind of related, and it has to do with the diameter of a circle. Oh, now that's a good circle there. If you have two chords in a circle, and one of them is the perpendicular bisector of the other. Now remember what perpendicular bisector means. A perpendicular bisector bisects a chord at a 90-degree angle. Okay, so we're going to focus on this chord here, the longer one, AB. Right? Since AB is a perpendicular bisector of the second chord, then we know that AB is the diameter. Right? So if you are told that those two sections, those two parts of that shorter chord are congruent, and you've got that right angle there, your conclusion is that AB is the diameter of the circle. Okay. Theorem 10.5, which is related to this, okay, another solid circle there. Then 10.5 says if you know you have a diameter, so we'll use AB again here, okay, and it bisects another chord, then it does so at a 90-degree angle, and these two arcs are going to be congruent. So 10.4 says if you know you've got the perpendicular bisector, you can conclude you have the diameter. Theorem 10.5 says if you know you have the diameter and you've got the congruent pieces of that chord, you can conclude the right angle and conclude that those other arcs, those associated arcs, are congruent as well. Okay. Finally, theorem 10.6. Draw another circle here. Okay. 3 solid circles back to back to back. Woo, on a roll. Theorem 10.6 says that you can conclude that 2 chords are congruent if they are equidistant from the center. Now, we've talked about kind of the shortest distance between 2 points. When we say they're equidistant from the center, what we're talking about here is if we draw perpendicular that's not very perpendicular. Sorry, I gotta redo that one. If we draw perpendicular segments from the center of the circle to the chords, probably like that, that's more perpendicular, and like this, okay? If these 2 segments are congruent, then the chords are equidistant from the center. So if we have A, B, C, and D here, segment AB, chord AB is congruent to chord CD because they are because they are equidistant from the center of the circle. And we can show they're equidistant by drawing those perpendicular segments from the center to each chord. And if they are congruent, then so are the chords themselves. Okay. An example of one, just so you can see the contrast here, 2 chords that would not be congruent. Okay, let's see, we have one going across like this, one kind of going more like that. Okay, the center of the circle is pretty much right there, right? These 2 segments are not congruent. Therefore, the chords are not equidistant. Therefore, they are not congruent chords. Okay. All right, so 10.3 has to do with congruent chords mean congruent arcs. 10.4 and 10.5 relate the diameter and another chord in a circle. 10.4, if you know you've got the perpendicular bisection of a second chord, then that first chord, that longer chord, is the diameter. 10.5, if you know you've got the diameter and you've got those congruent parts of that shorter chord, then you can conclude the right angle and the arcs are congruent. And 10.6, 2 chords within a circle are congruent if they are equidistant from the center of the circle. And it's those theorems that have prepared us to answer these questions down below. Answer each question and I identify which of the above theorems you reference. So just kind of get you started here, let's look at the first one. If the measure of arc AB, so let's identify arc AB, if that's 110 degrees, what is the measure of arc BC? Okay, so here's BC, and we're looking at that. Well, we can see that arc AB is formed by chord AB, and we can see that arc BC is formed by chord BC. And we also know that chord AB and BC are congruent. And because chords AB and BC are congruent, theorem 10.3 tells us that the arcs they create will also be congruent, and thus we can conclude that BC is 110 degrees. Okay, let's look at one a little more challenging perhaps, the one below it. If the measure of arc AC is 150, what is AB? Well, in this case, we're given arc AC is 150. No information about arcs AB or BC, yet we are supposed to solve for the measure of arc AB. Well, we do know that whatever AB is, we'll label it X, BC has to be the same thing because they're formed by congruent arcs, therefore the arcs themselves are congruent. So an equation that we can set up here is that the 150 degrees that we know plus 2 x's has to equal 360. And like we've talked about before, once you find that relationship, once you set up that equation, it's just back to algebra. and you can solve that equation for x, which x happens to be the measure of arc AB. Okay? Let's look at the second one here. What is the measure of arc CD? Okay? Let's look at what we have. We've got the diameter. We've got the right angle. So this is kind of another piece of Theorem 10.5 there. If you've got the diameter and you've got the right angle, you can then conclude that you've got these congruent pieces. I don't think I said that earlier. It works both ways. If you've got the diameter and the congruent pieces, you can conclude the right angle. If you've got the diameter and the right angle, you can conclude the congruent pieces. So there's kind of hand in hand there. But anyway, now that we've got this, we know that CD is congruent to ED. So since we're given a value for CD, 9x, and we're given a value for ED, 80 minus x, and we know the relationship between the two, that they're congruent, we can then solve for x, which isn't our actual answer here. We can solve for x, but then plug it into the expression that will give us the measure of arc CD. Okay? What is the measure of arc CBE, the one below that? Well, here, now we're kind of given the other one. Okay? If we know what arcs CD and DE are, and that there are 360 degrees in a circle, we can set up a relationship, set up an equation to solve for arc CBE. Last one here. What is CU? Well, let's take a look at what we have. We're given two chords in a circle, QR and ST. Both of them are 16, which means that since they are congruent, then these pieces here must be congruent as well, because in order for those arcs to be congruent, they have to be equidistant from the center of the circle. So 2x and 5x minus 9 are equal. There's a relationship you can use, right, to help you solve for CU. Then, the last one here says, what is the radius of circle C? I don't see a radius of circle C. Do you? Well, if we're not given a radius to circle C, let's draw a radius to circle C. And if I just draw a radius kind of going out like that, that's not going to be very helpful. What if I were to draw the radius of circle C to connect with point R? Why is that helpful? If you notice here, what I just created is a right triangle. A right triangle, which we already solved for CU. Because that's 16 there, that's going to be 8. And maybe we're looking to solve for the hypotenuse of that triangle, of that right triangle, what also happens to be the radius of circle C. So, no book homework. I answered one of them for you. At least got you started on the other 5 there. But this homework will be due for Monday. Monday and Wednesday of next week, we'll have live lessons. Again, tackling 2 more objectives, a recorded lesson on Thursday, and that's going to wrap up our unit on circles. Super quick, super quick. It's almost as if we took our last test and then we just turned around and took another one. Turned around like in a circle, turn around. Okay. Anyway, have a great weekend, folks. Thanks for watching. Don't forget to like and subscribe, and have a wonderful day.